Hello everyone, my name is Philippe Fulsac, and in this video I'm going to talk about an application of simple probability and combinatorics concepts to cipher breaking. So I'm going to focus more precisely on a form of substitution cipher called the Viginere cipher. And this type of cipher belongs to the category of so-called polyalphabetic ciphers. So the plan or map of this tutorial will be the following. First, I'm going to introduce the Viginere cipher. Okay. Well, I'm going to talk a little bit about the history of this cipher, explain how you can encode and decode um, encode plain text and decode ciphertext. And then, so encode and decode, how do you do this? And third, what I would like to show you is how do we actually analyze and break this cipher. Okay? So this part here is also called the cryptanalysis. Okay? And we are going to do all this with very simple, as I said, probability concept and combinatorics concepts. Okay, so it's a good application of basic probability theory. All right, so let's start with a little bit of history. So we are going to talk about a cipher that supposedly was invented by Blaise de Vigenère. He was a French diplomat born on April 5th, 1523 in France. And here is a picture of Blaise de Vigenère. Actually, Blaise traveled in several places in Europe, including in Italy. And he actually probably was probably in Italy. He actually was aware of work done by another cryptographist, Giovan Battista Bellasso. And Bellasso, in fact, is probably the true inventor of the cipher of Vigenère. Okay, so maybe there's a misattribution there, but it is known that de Vigenère improved and published books about this cipher, and also improved over the original cipher created by Giovan Battista Bellasso. Okay. Now, one question is, why would people and diplomats or humanists in this age of Renaissance be interested in cryptography? And one way to understand this is the relation between cryptography and, for example, religions. Okay. In particular, there is a very strong interest of esoteric form of religions, such as the Kabbalah, okay, in cryptography and in basically manipulation of alphabets. Okay, and that can be traced back to the concern with which Kabbalists express in regards of the name of God. So basically, the name of God is something very sacred, and we have to find. We cannot tell the name directly. We have to find indirect way to convey the meaning of the name of God. Okay. So mystics and Kabbalists have long been interested in cryptographic tools and in ways to encode basically the words of God and the name of God. Okay, so um, it is not uh, it is not very astonishing that um, this form of Jewish mysticism um, actually is found in the work of Blaise de Vigenère. Okay, you see here. You see here exactly the reason that I'm mentioning. Okay, the concern to keep the secret of the ineffable name Shem Amephora, and the preoccupation with creating other substitute divine names have led mystics to use various artifices and cryptographic constructions that are as many codes and grids that one must know how to decipher and read. So basically, only um, for these philosophers or Kabbalists, um, only them can decipher and understand the meaning of the Bible and of the Torah, okay, of the sacred books. So originally there are 22 letters in the Hebrew alphabet, and so people have been playing with this alphabet, both with the, the graphy, okay, the way the alphabet is written. Here's an example of choice of symbol for the Hebrew alphabet. It's called the Boule alphabet, okay, and it is used by Kabbalists. So you have the symbol, you have the name, and then there's probably a mystic meaning to all these letters and symbols. Okay. And in particular, you can find a special table in the work of De Vigenère, which is called the table of zeroths. Okay. And this actually this points to a cryptographic grid that was only deciphered by an ethnologist, David Roach, in 1989. So you can see that there's always a very interesting aspect to all these the roots of scientific findings. Okay. Now, let me show you how now the, the cipher of Vigenère works. We can do that very simply. Okay. And I'm going to show you that in just in a okay in my browser, my web browser. Okay. So I chose this site, this website. It's in French, but this is not a problem. I chose this site because it gives us a very clear animation that illustrates how the Vigenère cipher of Vigenère or Vigenère cipher works. Okay, so I could use a plain text such as "Hello guys." Okay, I'm just going to attach this. Hello guys. Okay, and how are you? So that could be the plain text that you may have to, of course, to separate the plain text, the words of the plain text by spaces. Doesn't matter too much really. Spaces play no role, but and I'm going to use a key to show you how this uses a key. The cipher uses a key to cipher the plain text and encode it with the help of this key into a ciphertext. So this is a plain text. This is a ciphertext. Just a word of your choice, maybe a key that you can easily remember. And now look at the cipher. Okay. So remember the key is king. So we start with the column K, column I, column N, column G, and now we continue K, I, N, G. Okay. So you can see how we actually we actually cycle the key. And imagine that we actually place the cycled key, king, 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 king. So we repeat the key, okay, underneath basically the plain text. Now, for each, if you look at this diagram, how does it work? So first you have the 26 letters of the French or English alphabet. They are the same, okay? So we are not talking about the Hebrew alphabet here. And what we do is we actually write the alphabet in the natural order, okay, and then we shift the alphabet cyclically by one, okay. So we here on the row B, okay, we have shifted the first row by one to the left, okay. So we continue. So we could also say we shift by -1 if you want, okay. If -1 is to the left and +1 is to the right. So we shift by -1, -2, -3, and so on. So you can see that we have exactly the same letters, okay, but they are shifted. And if you remember how the cipher of Caesar works, okay, you will recognize that each row is in fact a Caesar cipher. So this is a zero shift Caesar cipher, okay, in which the plain text A would be encoded by A, the and plain text B would be encoded by B, and so on, okay. For the Caesar cipher of the second row, the plain text letter A would be encoded by B, and so on. B would be encoded by C, and so on. Okay. And so what happens here, okay, is that when we so I'm just going to wait until we arrive at, okay, here. Okay, let's say we are, okay, we stop that. Okay, so again, let me cipher this, let me show you how this works. Okay, so for the first letter, okay, the first letter of the plain text is H. Okay, so you will see that here, okay, if okay, we have to encode the plain text letter H. Okay, so we use the corresponding letter in the key, which is K. Okay, so we use the K column here. So we are here, we are there. Okay, K column, and we use the H row. Okay, and so K column, H row, H row. And so we can see that the cipher letter that you should use is R. Okay. And in fact, okay, if I look down, okay, that's exactly, this is ciphertext, and the first letter is R. Okay. So similarly, second letter of the plain text is E. We have to use the key letter I. So we place ourselves in the column I. Okay, that's for the key. And for the row, we need to take row E. Okay, so row E, column I, row E, row E, column I. So we have a letter of M in the ciphertext. Okay, let me check that, M. Okay, and so on. You continue like this. So you can see how, sorry, I'm just going to repeat this. Okay, so that's basically the encoding that you get. Okay, each time you basically look, the ciphertext is at the intersection of the key column and the plain text letter row. Okay, and again we have to cycle this key, okay, to make sure that we know which key letter to use. Okay, so for O, for example, H-E-L-L, H-E-L-L. For O, I should use K, okay, to encode the key the key letter K to encode the plain text letter O. Okay, so now we know exactly how to encode a text from plain to cipher. Okay, a consequence of this method is what is called the polyalphabetic character of the method. Indeed, we are in fact the same letter, for example, O, okay, here, O is repeated here and there, but in the cipher, in the Caesar cipher, O would always be encoded by the same letter, okay? But here, because we are we are changing a row according to the secret key here, king, okay? Well, the same letter can be encoded by, depending on the position of the letter O, okay, it can be decided by a K column, a I column, a N column, or G column, okay. So there are actually 4 possibilities for letter O, okay. So there's a period, basically the length of the secret key, king, dictates a period in the encoding. Okay, and this is what we are going to use, okay, to attack this cipher. Okay, so let me now that we see how this works, okay, let me now try to see if we can write some R code to to um, well, to encode a message in R. Okay, so I'm going to come back to my uh, my R code here. Okay, and yeah, so and I'm going to show you how if we know the length of the key, okay, we can break the key. So let me show you how this can work. So first we can create some text, okay, some cipher text, okay. Here, I'm just going to use this cipher text as an example, okay. Okay. I have installed a library called secinr. It's not essential to use this library, but basically it's because I want to transform a word, okay, into a vector of characters, okay. It's a tradition to actually write plain text or cipher text in the case of the Viginere text with groups of 5 symbols separated by spaces. Okay, so this doesn't correspond to words. It's just they are just blocks, and this is a tradition in cryptography that we can use also. So if I want to transform this text to a vector of symbols, okay, I will have to actually suppress the white space and basically extract every letter in this sequence to an object. So for that, I'm going to reduce the white space to no space here, okay, in C. So I'm going to use the gsub function to do that. I could do that by hand, but I can win time and not have to write this myself. So here is the word now without the spaces, as you can see, okay. And now I'm just going to transform this. I load the library secinr, and I'm going to transform this to a vector. Okay. So if you look, I'm going to print this vector, city, and now I have a vector of characters. Okay. And so the good thing with that is that I can actually manipulate that in an easier way. Okay, so you can see how this cipher has about 450 letters there. Okay, so let's assume that we know the length of the key, and let's say that the length of the key has three as is 3. Okay, so basically we have a key of 3 letters, but we don't know the key. How can we guess it? So what we are going to do is we are going to take the text, the cipher text, CT, okay, and we are going to actually look at all letters at position 1, 2, or 3 modulo 3. Okay, so we use the given length of the key 3 here, okay, to create what we called cosets, 3 subsets of letters. So position 1 plus a multiple of 3, position 2 plus a multiple of 3, position 3 plus a multiple of 3. So we are going to get, of course, 3 blocks. So let's do that. So I'm actually I'm creating the indexes of these, the vector of positions of these blocks. And now, for example, if I want to look at the block, okay, that is located at position 1 plus a multiple of 3, this is the first block or first coset. Okay. And of course, I have about 3 times less letters in this block. Okay. And so now what I'm going to do is I'm going to make an analysis of frequencies. Okay. So I'm going to take and basically I expect, okay, because the letter has the secret key has a length of k of 3. Okay. I basically here I am always using the same secret letter, right? For example, if the secret word is boy, okay, BOY, then by looking only at position ones, okay, modulo 3, I'm always going to use the scissor cipher based on the letter B. Okay, and for coset number 2, I would use letter O, and for coset number 3, I will use letter Y. Okay, so what I will do is I'm going to use I can do a frequency analysis very easily. Let me show you how this works. So I can basically I'm going to count. I'm just simply going to count how many each let how many let how many times letters occur in the first coset. Okay, so here we are. I have an example of that. A is found 1 time, C is found 12 times, and so on. Okay, so that's in the first coset. And of course, now, okay, the thing is that uh, the most frequent uh, letter here, the letter that occurs the most frequently is V. Okay, 25 times, and this is by far. So the idea here is that we are going to use the fact that we know that the target language of this cipher, okay, cipher text is English, okay. So I'm going to assume that I know that the plain text is in English, okay. And so I am going to map this letter or decode this letter as the most frequent letter in English, okay. So I use a prior knowledge for that. I'm going to assume that the most frequent letter in English is E. So I can actually find again, I can use which max to find which position in the table maximizes frequency, and I will find that this is the letter V. Okay. Okay. So this is now doing that programmatically instead of just doing it by observation. Okay. So I find again that it is this position here that maximizes um, the frequency. So the letter in IM1, position IM1, should be encoded as an E. Okay. So this is what I'm going to do. Okay. I am going to say that, okay, I found this letter here. Okay. And this is the letter that stays in that is in position 22. Okay. So if I look at that, okay, what is okay? I can use. In fact, I have in R. I can use the vector letters, which contains the lowercase letters from A to Z. Okay, without repetition. Okay. And I can ask, okay, I can ask which position is the position of V in this array. And that's letter V, okay, 22. Letter V is in position 22. Now I'm going to now map this, okay, to the most frequent letter, and clearly if you count the position of E, okay, you will find that it is of course 5 in the English alphabet, and so same actually it would be the same in French. And so because I have the position of the plain text word and the ciphertext, which correspond to the plain text word, I can say that my Caesar cipher, okay, for block 1 would be a cipher that shifts positions by that amount, IW1 minus IW2. So basically, okay, I am going, for example, to if I want to know okay, what is the first letter of key? It should be an R. Okay. Okay. So we have NA letter. The length of the alphabet is NA 26. Okay. Let me show you that this is the case. And what I'm going to do is I'm going to save the text, the cipher text, to a new array here. Okay. And I'm going to progressively decode the ciphertext. Okay. Using my knowledge of using my knowledge of the shift. Okay. So I can easily you see, I can easily select a letter, for example. Okay. For example, if I take a letter in city, which is CTD of say 1, and I ask, where it is as a number. Okay, I can just retrieve the position in the letters arrays. So this is an array of uppercase letters. Okay, so so CTL, I'm going to print it. If CTL is J, okay, the position is 10 in letters. Okay. So okay, I'm going to now decode. Okay. I know the shift. I've calculated the shift. So I initialize my ciphertext decoded CTD, okay, to CTD IN, okay, like input. Okay. Now I loop over all the position. I take the letter in the ciphertext, okay, and I only take the position in the first coset, okay. and I know how to decode this. I just shift the position. I first find the position and shift the position by sh. Okay. If I find that I've shifted too much, the shift must be cyclic. So if I find a negative number, I add the number of characters in my alphabet. Okay. And so this actually, and here I update my deciphered text. Okay. So the result of this is a new version of the text where I have deciphered all the letters in block one, in cassette one. So let's run this. Okay, and now, okay, again, S is deciphered. Okay, I should put a blue, or I should put a color here, maybe maybe I'll do that later. But basically, I have deciphered every letter in position that is equal to 1 modulo 3. Okay, so this is my deciphered letter. Not deciphered yet, not deciphered yet. This is the other deciphered letter, and so on. Okay, so I'm going to do the same for all the other cassettes. I have 2 other cassettes to decipher. Okay, so again, I do the same game. Okay, I try to identify the second uh, max letter. I find it's S. Okay, and I calculate my shift exactly as I did before. Okay, so the second I've guessed now the second secret letter, okay, in my secret keyword, okay, and it's an O. So now my secret keyword, I know it's R, O, and something that I still don't know. I have enough information now because I have the second secret letter here. I have enough information. Uh, I know that the shift is 14, okay, because I need to go. I encode 5 by 19 basically, so that's 5 plus 14, okay, or E is encoded by S basically, okay. And so I use my shift, my new scissor alpha, my scissor cipher, okay, to decode cassette number 2. Okay, so it's exactly the same type of code. Okay, and I reinitialize my deciphered code to the state that I was in before. Okay, and I can decipher my code. Okay, at position 2, every position in cassette 2, which is the position is 2 modulo 3. Now I have actually 2. This is deciphered, this is deciphered, this is not deciphered. Deciphered, deciphered, not deciphered. Okay. So I'm now going to finish, okay, and decipher the third block. Okay. So again I look at the table for this block here, okay, and here there's an ambiguity because the maximal frequency, I have 2 options. So what I did is I inspected both the C option and I inspected the M option, and I found that actually C didn't give me any results, so I concentrate on the M option. Okay, so I find that M is the letter of interest, and I can easily reconstruct the shifting value, okay, to be 8, because I must encode an E by letter number 13M. Okay, so the shift for the third Caesar cipher is 8, and I can use this shift now, okay, to find the third letter, and the third letter is an I. Now, okay, I know that the key is Roy, okay, and so the secret key is Roy, 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 Roy. Okay, Roi means king in French. In fact, the target language here, I said it was English, but it's not English. It's actually French. Okay, so now I can use my knowledge of this third shift here, okay, to decode the last block, and I should be able to read that my message in clear now. So my message is now fully decoded. My message is fully decoded, and well, we can actually we can recompose it as a string, and this is the message. Okay. So if you know French, you will recognize what this means. Okay. We are almost done. We have to fix a few details. We have to find the blanks. So here we are. And maybe add the diacritics. Okay. So, s'ouvrit pour Nicole une phase épuisante, l'inconscient ligoté par l'orgueil. Okay. So for that I didn't do this step in R. Okay, I could, but I didn't. I used to recognize this text. I use a tool online, which is you can find here. Okay, so the tool is called Zodiac, and basically I placed this text, and I got the text accentuated with accents. Okay, here. Okay, so that's the result of Zodiac. Okay, so Zodiac is able to add the diacritics. Okay, and now, last but not least, maybe if you want to understand what this means in English, we can use DeepL or any translation tool to translate the text to English. Okay, so that translate as an exhausting phase began for Nicole, the unconscious, bound by pride, cracked. She had never dreamed so much. Drowned faces surfaced on the surface of a calm sea. She could see the green eyes opening and closing like the slow valves of a shell between two waters. Sleep washed away these recumbent faces. Okay, so we went, okay, from the cipher. Okay, so what did we achieve? So we went from the cipher text, where we had no idea of what the cipher text meant. I'm going to show you the cipher text again. So we went from there, okay, to fully decoding of the message. However, there was a catch, okay, and the catch was that we had to know the key lengths, okay. So that is the first part of the analysis, okay. Given the key lengths, how do we break the key? And I hope you understand how this is done now, okay. Now, okay, we need to go and complete our cryptanalysis, okay, with a method for inferring the length of the key, okay, which was actually critical, okay. So now we need to know how to break the length of the key. We assume we knew the key length. How can we infer it? So we are going to use a method that is based on a concept that is called the index of coincidence. Okay, and I'm going to show you how this is defined and how we can use the index of coincidence to actually break the length of the key. So the index of coincidence IC or IOC, okay, uh, is actually defined in the following way. If we give any text string, okay, so let's say a long sequence of letters, the index of coincidence IC or IOC, that's for the notation, is simply the probability that two randomly selected letters independently and randomly selected letters are equal. Okay, so the idea is that if we code X a letter extracted from randomly extracted from the text, and Y a letter randomly extracted from the text independently of X, IC is the probability that X is equal to Y. Okay. So here we are talking about probability, as I had have announced that we would use probabilities. Here we are. So let's assume now, okay, so we need to calculate the probability, the IC, we simply need to have a model for the frequencies of letters, okay? So let's assume that the letter AI, so for example, in AI could be A or B or C or D and so on, okay? So we could say that I is the ith letter in an alphabet, A, okay? Or L. Let's say that this symbol appears ni times. So I'm just counting how many times it appears in the text. Okay. Then we can of course estimate the probability of that the letter X is AI if it's uniformly chosen in the text as the number of times that you see ni divided by the total number of symbols in the or the length of the sequence. Okay, so that's actually applying a very simple concept of probability theory. Okay, so we basically estimate the probability that the letter is I, or the probability that if we pick a random letter in the text, okay, and the text has a length of n, okay, and if ni places where the letter is I, well, clearly this is a good estimator called the empirical probability of letter I. Now, suppose that we look at two letters. So, and let's concentrate on this letter AI, okay? How many choices do we have for to pick AI? Ni choices. And once AI is picked, how many choices do we have to again pick AI in the text? Well, clearly we have Ni minus 1 copies of AI that remain, okay? So basically, we can see that the probability of pulling, okay, twice the same letter is basically given by this formula. 1 divided by n times n minus 1. That's the number of ways to create a sequence of two distinct two letters or two symbols. Okay. Once we have we have n choices for the first symbol, and n minus 1 choices once the first symbol has been drawn. Okay. And here we sum, of course, over all letters, okay? Because for each letter, we could have AA or BB or CC or DD and so on, okay? So basically, we have, in English, we'd have 26 terms here, okay? So that's how we can calculate the index of coincidence, okay? And of course, if n, the sequence length is large compared to all the ni's, then we will have, we can neglect the minus 1. And so basically, we can see that if we, we neglect all the minus 1s in this formula, here and there, okay, we can easily see that this is the same as the sum of the ni divided by n squared. In other words, basically, the asymptotic estimation of the index of coincidence is this. So if we have a language in which we know the distribution of frequencies of letters, pi, okay, That is, we know the probability mass function of of each letters, basically, of each letter. Okay. Letter 1 is, say, symbolized by 1, letter 2 by 2, and so on. Okay. Then we can calculate this index of coincidence like this. Okay. And if we don't know the PI exactly, we can approximate the PI by having a sequence of written in the target language. Okay, so how can we now break the key lengths? Okay, I'm going to show you two methods. So either we can actually directly estimate the key lengths. Can you obtain a formula for K if we know the target language? So the idea is yes. Okay, and what we are going to do is we are going basically to use we are going to use either uh, a target language or a random choice, okay? And we can easily show, okay, that the index of coincidence, an estimate of the index of coincidence, is a mixture of these two, okay? So regard IR and IL as two prior probabilities, okay? This is, say the target language, such as English or French, okay? And this is a random gibberish, okay, in which each letter it's a language where each letter has the same probability, okay? So if we have IL, IR, and if we observe IC, okay, we can easily take K and get K out of, in a closed formula, get K out of this formula, okay? And so we can extract K from this formula, okay? So I'm not going to do that, okay? I can leave it to you, okay? Easy to actually okay? I leave that as an exercise to you. Okay? Exercise, estimate K, calculate formula that estimates K from all other quantity, from all other quantities, okay? So basically, the formula will be something like a function of C, L, and so on, okay? Okay, so basically this is it's very easy to do. So again, you know the language, you know the cipher text, okay? And you can find from this formula, you can just inverse K from this formula, okay? Now, I'm not going to use this method, which is not always very accurate, okay? What I'm going to do is I'm going to use another method of estimation of the length key. And I'm going to ask for a value of K, okay? And the idea here is will be different. I'm going to ask for a value that basically maximizes the index of coincidence. So here the idea is different, okay? I am going to calculate the index of coincidence for each coset, okay? So if I hypothesize that I have a length K of L, okay? For example, L equal 2 or 3 or 4, okay? I'm going to try a length of, I can also use 1, okay? So I'm going to play basically the length of the key, okay, systematically, 1, 2, 3, 4, 5, and so on, okay? And for each, I am going to calculate the index of coincidence of each coset. And I can easily do that by simply summing the sum of square frequencies of symbols for each coset. Okay, empirical frequencies. Okay, so I'm going to do that, and the idea is that the true the true the true value of LK should actually occur for when the index of coincidence is maximized. Okay, so let's do that. So again, remember that we can analyze coset like this. Okay, and I'm going to use this example for to break this this length. Again, you can always use table to analyze the frequencies. Okay, so you can calculate the NIs. And you can calculate the index of coincidence. Okay, so here we find a very high index of coincidence. Okay, and I in fact created a little function here. Okay, to be able to calculate that get IC. Okay, returns the index of coincidence. And you can see here it's just calculated from the formula, sum of ni times ni minus 1 divided by n times n minus 1. Okay, and I can well, the beauty of this little function here is that I can pass text directly. Okay, and it extracts the index of coincidence. Okay, so again, so here it is. Okay, if I apply my function to example 1, this text here, the text that I gave above, okay, this text here, okay, and you can see this text looks like it has been it has some it looks like a partially decoded text. Okay, you can see some English here. There are ways. Okay, it doesn't look completely English, but it doesn't look certainly doesn't look random. Okay, so this is why the index of coincidence is so high. Okay, and if it was really random, we would get a much lower value. In fact, we can easily check that. For example, here, let's take another example. Okay. Well, this, sorry, uh, one here. Okay, so you can see here that this doesn't look English, looks much more random, and therefore, when I calculate the index of coincidence, it is the value is considerably smaller than this one. Now, considerably, okay, smaller, you have to, I mean, if you try text precisely as I do here, okay, you will see what we mean by considerably smaller, okay? And that's now, okay, we can try another one here. Let's take this text here. Okay, so I'm going to take this text and I am now going to do so actually, and this is another one here, another example, just a sec. And well, I need to take again one here to say that I'm using an uppercase alphabet. And here again, you can see that this is very high. In fact, simply because this, in fact, is a cipher encryption, a Caesar encryption, so a monoalphabetic shift simply of English. Okay, so therefore, it's quite logical to find a high value for the coincidence index. Okay, so the high value of the coincidence index here tells me that this is English and English translated by or ciphered through a simple encrypted in a monoalphabet by a monoalphabetic cipher. Okay, and I just decode this very quickly from the amount of the how high the this is. It's comparable, totally comparable. In fact, it's equal to the value I would get from the plain text of this in English. Okay. All right. So the reason for that high value of IC is that it is encrypted with a monoalphabetic cipher. Okay. Now okay, we are ready. Okay, ready to use the IC method break LK. Okay, so I'm going to do the exercise on this cipher on this cipher text. So I just give you this cipher text, one cipher text. I don't tell you anything, and I'm asking what is the length of the key. Okay, I'm going to assume that I use a Viginere cipher. So, okay, I encode that as a vector. Well, or rather, I just transform this into the sequence of letters. Now I try LK equal 1, okay, and I simply get my value for IC1, okay, and I get that value. Now I can try LK equal 2, and for LK equal 2, okay, now I have two cosets. So I'm going to calculate IC for both cassettes. I have two values. And here are the two values. Okay. Try LK equals 3. And here we are. Okay. So you can notice that AK equals 3 has a much higher value than the IC has a much higher value for all cassettes. Okay. So LK equals 3 sounds much better than the two others. Let's try AK equals 4. And here, okay, we have 4 cassettes to encode and the value of IC, okay, drops down dramatically. So we can continue like this. You can try other values and you will see that LK equals 3 gives you the best result. So we have broken lengths. Okay? It is 3. Okay. Now let's actually again guess the key. We already have seen a method for guessing the key. Okay, I've showed you how to guess the roi key in French. Okay, now I'm going again to break the key, knowing that the length of the secret key is 3. Okay, I'm going to guess the letters of the secret key by using another method, which is the method of chi-square. Okay. So I'm going to use again a prior, the frequency distribution of letters, PMF in English. Okay. And that's my prior. So that's basically the knowledge of the frequency of A, B, C in percent. Okay. In English. Actually, I am going to, well, I am going to take, I am going to, sorry, normalize. Need to normalize. I need to normalize my. Okay. I will normalize my normalize my frequencies, sorry. So basically f L equal to f En divided by sum of f En, okay. And I'm going to show you how we can use the chi-square method, okay, to decipher to decode the message, the key, the okay, the key. So here we are, okay. So we have the frequencies of our target alphabet. The length of the alphabet is 26, okay, and we can normalize the frequencies, okay. And for example, the frequency of the third letter in English is this, okay. That's a probability or an empirical probability. Now, what I did is I wrote a function to apply the chi-square method. So the idea is that I will actually pass a word and pass the model of frequency, this model here, okay? So this method here will return the chi-squared value for any sequence of text encoded as a word, okay? Actually not as encoded as a word, but as encoded as a vector of characters, okay? So the function works like this. I extract the length of the vector of characters that I want to calculate the chi-square of, okay? I initialize the chi-square value to 0. NA is the length of my alphabet, okay? And which is 26 in English, okay? And now for each symbol in the alphabet, okay, I calculate the observed frequency of this letter, okay, in W, and I use this observed frequency, okay, and I compare that to my model, okay, and so I calculate the chi-square, okay, and so the closer my frequencies are from to my model, okay, the smaller the chi-square value, and this will so basically I'm going to use the smallness of the chi-square value to drive my inference, okay. So let's do that. Let's define this function. And now let's try to calculate it, okay? So what I will do is I will again encode my 3 cosets, okay? So uh, remember how I calculate the cosets, okay? So I am going to take this, I'm going to take this plain text here, okay? And I'm going to encode it with this keyword, secret keyword, okay? I know that I can guess the length of the key, okay, by applying the method that I described before, okay? So now I can just, well, try to decipher the 3 letters BOY by the method of by the method of the chi-square, okay? So I define my 3 cosets here, as I did before. I use 3 because I've broken, I assume they've broken the length of the key. It's 3, okay? And now what I do is I create a shift function, okay, just to decode any word, okay, in a Caesar alphabet. And so now I can actually easily get the IC value, not the IC value, the chi-square value for each coset. Okay. So instead of taking the cosets themselves, which would be shifting by 0, okay, I can try every shift. Okay. So I can shift by 0, by -1, by -2, and so on. Okay. So I give an example of that. Okay. So here are 3 values of chi-square values obtained by shifting by -2. Okay. And so basically, I will construct a matrix like this, okay, by trying all the shifts, which are from 0 to 25. So I'm going to shift by 0, by -1, by -2, and so on. Okay. So I'm going to explore every possible scissor cipher and get the chi-square value. Okay. I'm going to store that in a matrix MCS. And when I'm done, okay, I'm going to sort the value, okay, to find the smallest values, which are the 3 first smallest value for chi-squared. And I can extract the letters like this. Okay. So here we are. I automatically find, okay, how to recompose the letters of the secret key, BOY. These letters are obtained by taking the 3 letters that minimize the chi-square, the distance to my language model, if you want. Okay. So now I can actually I can easily decode my text. Okay. I know that this is a ciphertext, okay, and I will use my key B or Y, and here what I do is I write a routine to decode my text, okay. So I start with an empty text here, and I append each time, okay, if J is 0, is in position 1, modulo 3, I use the first letter of the secret key. If it's in position 2, I use the second letter. If it's position 3 or 0 modulo 3, I use the third letter. Okay. And I use my decode function, okay, to just Caesar shift the encoded the encoded text, the encoded letter text. And so I find that the plain text is this, which is exactly what I wanted to decode. Okay. So as an exercise, you can try to decode the following message. Okay. And I'm just going to tell you nothing. It's text encoding encoded with a Viginere cipher. And I'm not going to tell you either the length of the key or the secret key. You can all deduce this or infer this by yourself using the method that I've described in this video. So to summarize, okay, in this video, uh, I have showed you how to break the Viginere cipher. I hope this video has been interesting, and I stop here. Bye for now.